So officially, welcome to the NICKEFFECT webinar series, where we would like to share knowledge that's been generated throughout the project, but also really interesting topics that are relevant to the project's field. Today we have Jordi Sort Viñas. He's a professor at the Autonomous University of Barcelona, and he will be sharing his knowledge about Magneto-Ionics for energy-efficient, brain-inspired memory devices. Before I give any word to Jordi, I would like to mention that please mute your microphone where you're not speaking. We would not like to interrupt the speech. Of course, to mention if you are speaking during the Q&A session, and of course the speaker to have the cameras on. Once, if you have some questions at the end, we will have a session for that. Please raise your hand or comment in the chat your question, and it will be addressed. If you have a question about something that Jordi mentions during the presentation, please, of course, write it down, and then we will be addressing it towards the end of today's webinar. As I mentioned, so after this brief introduction, Jordi will take the spotlight, and then we will be having the Q&A session and the conclusion of the webinar. So, Jordi, the floor is all yours. You can share your screen and share all the knowledge you have with us.
Do you see it? Everything okay?
Yes, perfectly, Jordi. The floor is all yours.
Thank you very much. Thank you to the listeners for being here. Today I'm going to talk about Magneto-Ionics for energy-efficient, brain-inspired memory devices. I would like to first maybe put this thing. So I would like to first acknowledge the collaborators, people from my own group here at the Physics Department of Autonomous University of Barcelona, but also some collaborators from the Catalan Institute of Nanoscience and Nanotechnology, Georgetown University, the Institute of Radiation Physics in Rosendorf, and SpinTech in Grenoble. So the outline of my presentation will be as follows. First, I will introduce the concept of big data and what are the challenges associated especially with energy efficiency. Then I will move towards the mechanisms for voltage control of magnetism. I will explain what is Magneto-Ionics, and I will show you that Magneto-Ionics has potential applications in neuromorphic computing. And after this introduction, I will show some results from our group, comparing first of all oxygen versus nitrogen Magneto-Ionics. I will show that this magneto-ionic effect is able to induce an on-off switching of ferromagnetic properties of materials. Then I will compare binary with ternary compounds. I will show you that we can induce these effects in a wireless manner. I will talk briefly about what are magneto-ionic vortices, and finally some synaptic applications. And I will end up with some conclusions. So you all know that now, you may know that now we are entering into what is called Society 5.0, and this follows from, let's say, the evolution of the humanity, starting from Society 1.0, hunting society, then was an agrarian society. In the 18th century, we had the Industrial Revolution, Industrial Society. Last century, we were in the Information Technology Society, and now we are entering into something new in which words like Internet of Things, artificial intelligence, big data, machine learning start to appear and start to be in our everyday lives. So to enter this Society 5.0, it is necessary to be aware that we are surrounded by a huge amount of data. Nowadays, at present, we produce about 200 zettabytes of data. That's about 10 to the 23 bytes of data. And this, of course, is a bit challenging for several aspects, as you can imagine. First of all, this huge amount of data needs to be stored somehow. We need to make compatible different variety of formats of data, optical media, magnetic media, transistors, and so on. We need to take care about the speed of writing and reading the information, energy efficiency, and security. That means protecting the data against security threats, against cyber attacks. So as you can see here, in parallel to the increase of the amount of data, there is now an increase in the next few years in the energy consumption. This energy consumption related to information technologies by 2030 will be about 20% the global energy consumption in all aspects of our life. So that's not an insignificant number. And this energy will be spent especially in networks, production of ICTs, consumer devices, and data centers. So taking this into account and looking a bit towards the past, you can see that in order to cope with this growing amount of data and the energy efficiency, actually every about 20 years, there is a need to increase the energy efficiency by 2 orders of magnitude. So if we go back to 1980s, you can see that as a function of time, the amount of energy needed to perform one operation has been decreased. So in 1980 it was about 10 to minus 7 joule, and the target in 2035 is to reach 10 to minus 18 joules. So this is needed in order to be able to cope with the technological progress in information technologies. And the problem is that the current computers are not able to reach these values. In order to reach these values, we need to enter into what is called a neuromorphic target, or basically try to emulate biological neurons, because biological neurons really spend very little amount of energy. So I'll go back to this point a bit later. So just to put this in perspective, I want to mention here this example of chess playing a competition between Kasparov and Deep Blue. Kasparov, you know, it was a very famous player of chess. And there were 3 games against Deep Blue. Deep Blue is an artificial intelligence software that was developed in 1997. And there were 3 games, and finally Deep Blue won. But here, what I want to emphasize is the energy consumption of Kasparov and Deep Blue. So Kasparov was spending in those 2 hours of the game about 20 watts, whereas Deep Blue was spending 1,000 watts. So basically, in 2 hours, the Deep Blue spent the energy of Kasparov's brain of more than 2 or 3 weeks. So you can see that this starts to be a little bit a problem. And it's even worse nowadays with the ChatGPT, data centers, and so on, that consume millions of watts. So they consume million times more energy than the brain to mimic the brain. So you can see that there is some success in emulating some artificial neural networks and so on, but the problem is the energy consumption. And why is that? One of the reasons, if we go into magnetism, is that in order to write information, here at the end of this writing head, there is a small electromagnet, and the way the information is written is through electric currents. So this electric current can be positive or negative, and depending on the direction of the current, you can write bits to the left or to the right, and we have the ones and zeros and so on. But the problem is that when you have a current flowing in a wire, as you know, the material, the wire gets warm. This is the Joule heating effect. So actually, in data centers, about 40% of the total energy that reaches the data center is not used, and it's just wasted in the form of heat. So that's, of course, not efficient in terms of energy. And this is well known by companies. Here you can see refrigerating system from Google, data servers with cold water. And of course, this costs money to build all this. So that's why some companies prefer to bring their data centers under the ocean, for example, Microsoft, or some other companies like Facebook like to install their servers in cold countries like Sweden or Finland. So what we can do in the laboratory to try to minimize this problem? So we could think of changing a bit the paradigm of writing magnetic data from an electromagnet where, as I have said, there is a current flowing and you have the Joule heating effect, to something looking more like a capacitor, in which one of the plates of the capacitor could be a magnetic material. And here what we want to do is to apply just a voltage, bringing the current virtually to zero, just accumulating electrostatic charges, and see if this voltage can tune the magnetic properties, eventually writing information. If we could do that, then we would minimize the Joule heating effect. Now the question, of course, is this possible? Is it possible to control magnetism with voltage? And this brings us to the so-called converse magnetoelectric effect, which is not something new. Actually, already in 1894, Pierre Curie predicted the occurrence of simultaneous ferroelectric ferromagnetic orders in some materials, intrinsic multiferroelectricity, if you want. And this was the first time that actually magnetoelectric effect was observed using chromium oxide in 1961. And after that, there has been a large variety of materials that show this combined action or combined synergy between electricity and magnetism in composites, for example, particulate composites, laminated composites, virtually aligned nanostructures, nanoporous alloys, strain gradient mediated materials, and so on. And there are several mechanisms actually to control magnetism with voltage. We can start with what I was commenting, these multiferroic materials, in which ferroelectric and ferromagnetic orders are mutually coupled, and they can be single-phase materials or can be heterostructures. Single-phase materials are scarce, especially showing multiferroic properties at room temperature. That is why heterostructures are commonly fabricated. And here what happens is that when you apply voltage, the ferroelectric material, which is also piezo, deforms, and this deformation is then transferred through the interface with the magnetostrictive material, changing the properties. But of course, this has a problem of fatigue. If you deform the material many times, at the end it breaks. There are other mechanisms to control magnetism with voltage besides these two, which are, for example, surface charging. If you have an ultra-thin metallic film or a semiconductor and you accumulate electrostatic charges, then these charges can modify the electronic band structure, eventually leading to changes in the magnetic properties, anisotropy, coercivity, and so on. But we can move a bit further. We can think of electrochemical reactions. This is quite simple. For example, if you imagine an iron foil that you immerse in water and you apply voltage and the iron will get oxidized, of course, this oxidation will change the magnetic properties of iron. But we can make it a little bit more sophisticated. For example, you can think of intercalating ions inside oxides or metals in a controlled manner. And this, for example, iron oxide immersed in a lithium battery, you apply voltage and the lithium cations will enter the iron oxide structure, modifying the properties. Or you can think of exchanging ions between a metal and a metal oxide in a composite material. All this ion intercalation and ion migration, changing the magnetic properties of materials, is what is called Magneto-Ionics and is what I'm going to talk in this presentation. Then, interestingly, in 2019, there was this work by the group of Misra and collaborators in which they showed that this magneto-ionic effect can be used to mimic synaptic functionalities. They studied what happened in cobalt with gadolinium oxide when you apply voltage, negative or positive, and they saw that ions, oxygen ions, can move from gadolinium oxide to cobalt or vice versa, depending on the voltage polarity. And these are indicated, these blue spheres here. And this motion of oxygen between the two layers caused either an increase or a decrease of the Hall resistance, anisotropic Hall effect. And this mimics the learning and forgetting processes in the brain. Later on, some other groups, for example, the group of Sebastian van Dijken or our own group, have shown that you can use other ways of modulating synaptic weight. For example, skyrmions in this material. Here, the ions that move are lithium cations that are entering this structure, or they are adsorbed at the interface of this iron core boron, modifying the density of a skyrmion, which are these little white circles that you can see. So they modify the density and also the size of the skyrmions, and this allows to modulate the synaptic weight for reservoir computing. And why the brain is so efficient? Because computers that we are commonly familiarized with, they have two components, the memory array, the hard disk drive, and the processor. And the problem is that these two units need to be in continuous contact, let's say, exchanging information. So this transfer of data between the memory array and the processor takes time and energy, and that is why it's not very efficient. Our brain actually does not work like this. Our brain has what is called in-memory computing. It means that the synapses and the neurons, at the same time, they are able to store the data and process the data. And that's why the brain is so efficient, as I have shown before with the example of Kasparov, only a power of 20 watts. Okay, now I would like to show what we have done in the last 7-8 years in this topic. I will start mentioning that many times we use what is called electrolyte gating. That means to immerse our material of interest most of the times in a liquid, in which the liquid is able to generate what is called the electric double layer, which is an ultra-narrow dielectric that surrounds all the material. Even if there is roughness, it just conformally coats the surface, the interface between the solid and the liquid. And this electric double layer, which is very narrow, allows to create extremely high electric fields at the surface of the order of megavolt per centimeter. And this is why we have such huge electric field is able to produce this motion of ions inside the material. And you may think that working with a liquid, it might be a problem to mimic the brain, but actually don't forget that our brain is 90% water. So it's not that bad in that aspect. So let's start with a very basic result that we obtained in 2017, 2018, which is shown here. This basically is what happens in a thin film of 100 nanometers, cobalt oxide produced by atomic layer deposition, that initially is paramagnetic. So as prepared, this is the black curve here. It's no hysteresis loop, non-magnetic. And one of my PhD students, Alberto Quintana, applied for 1 hour a voltage of minus 10 volt. And he could observe that after waiting 1 hour there, if you measure, you can see clear hysteresis loop. And then if you apply 20 volts for another hour, you recover the paramagnetic state, this red curve here. So we called this a Magneto-Ionics switch because we can switch on and switch off the ferromagnetic properties of the material in a similar way as one could switch on and off the light of a lamp. So that's funny, that's, let's say, an interesting effect, but the problem here is the speed. You see that we need 1 hour to switch on and to switch off. So in the following, what we did is to try to reduce this time significantly. But first, let me explain why the cobalt oxide becomes magnetic. And as you can imagine, after my introduction, here the idea is that when we apply voltage, the oxygen ions may migrate from the film and actually may create some clusters, metallic clusters of cobalt, which is magnetic. And this was confirmed actually by high resolution TEM. You can see here on the panel JMB, the as prepared state basically is a mixture of cobalt 304 and cobalt monoxide, so non-magnetic phases. But after we apply negative voltage for some time, we start seeing these additional spots that correspond to magnetic hexagonal cobalt, and we can even detect where these crystals are. If we have a look at the compositional maps obtained by EELS, you can see that the as prepared film is completely homogeneous. So this is the cobalt mapping, this is the oxygen mapping. Everything is homogeneous, but after treating with a negative voltage, we see some regions that are becoming enriched in oxygen and some regions that become enriched in cobalt, sometimes, quite often actually, following this direction perpendicular to the film. And this is because these grains in cobalt oxide are columnar, and the ions prefer to move along the edges or the boundaries of these grains, so perpendicular to the film. Now, the problem of cobalt oxide is that it is very slow, as I have shown. So we thought, or maybe another material could be better. And we thought of cobalt nitride. Cobalt nitride is also cubic. Actually, the advantage of cobalt nitride is that the electronegativity between nitrogen and cobalt is it's lower actually than between oxygen and cobalt. So in other words, cobalt nitride bonds are weaker than cobalt oxide bonds. So we did the experiment. We tried to see what happens in cobalt nitride if we compare thicknesses of cobalt oxide and cobalt nitride the same. So in our case here, as I'm showing, it's 85 nanometer. And this is how the magnetization, saturation magnetization, increases as a function of time. So you can see for cobalt oxide that when we apply voltage here at the instant zero, the magnetization starts to increase, and it increases even for several hours. After 3-4 hours, it's still increasing. However, for cobalt nitride, everything happens in the first minutes. So cobalt nitride is indeed faster than cobalt oxide. And we can induce this Magneto-Ionics switch applying relatively low voltage of -4 volt, -4 plus 4 volt. So cobalt nitride actually shows good cyclability here in blue at these voltages of 4 volt. However, for cobalt oxide at 4 volt, there is no cyclability, and we need to apply 8 volts in order to see this cyclability. Okay, next, what we did is to check also compositionally what happens in cobalt nitride, and also we tried with iron nitride. And we saw an interesting effect that I will expand a bit later, which is this planar front. So we start with this layer that at the beginning is homogeneous, and after treating with voltage, we subdivide the material into two regions, one of them that is more nitrogen than the other. And this is different than with cobalt oxide, that basically we had these perpendicular channels where oxygen was moving. So nitrogen seems to be released to the liquid in a layer-by-layer fashion, and it generates this planar front. And this is important for applications, as I will show you later. But going back to the speed, what we did next is to compare cobalt nitride films of different thicknesses. And what we did is to decrease the thickness from 200 nanometers to 5 nanometers. And here you can see for 200 nanometers that it takes, applying this minus 25 volt, it takes about 5 minutes to get a significant magnetization. But with 5 nanometer, everything happens in less than 1 minute. And actually, if we zoom here at this starting, let's see, the first points, you can see, this is actually shown here on the right, you can see that after 1 second for 5 nanometer cobalt nitride, we already induce some magneto-ionic effect. So basically what we have achieved here is going from about 1 hour in our original experiment of cobalt oxide to less than 1 second, changing from cobalt oxide to cobalt nitride and decreasing the thickness to 5 nanometers. Now, in the next slide, what I will show is that it's even possible to further improve the effects, moving from binary cobalt nitride to ternary compounds. Here we added manganese, for example. An addition of manganese into cobalt nitride makes the film more amorphous, and it improves the effect. So here I compare, again, the same thing as cobalt nitride, cobalt manganese nitride. You can see that cobalt nitride has lower magneto-ionics than cobalt manganese nitride. And moreover, the cyclability, applying these 20 volts, is 25 volts, is much better with cobalt manganese nitride than with cobalt nitride, where we lose the cyclability after 3 cycles. And one of the reasons why it's better with manganese addition is that the energy barrier to incorporate nitrogen in cobalt manganese is lower than for cobalt. So you can see here with cobalt, the energy, let's say, difference between this maximum and the minimum is larger than compared to cobalt manganese, which are the red or the blue curves. But manganese itself is non-magnetic. So we thought maybe adding, instead of manganese, adding iron could be even a better choice. So we next studied the ternary cobalt iron nitride compound, and we saw that when we induce magneto-ionics, actually the best composition, so here is as a function of iron content, this discontinuous line is cobalt nitride, and then when we add iron, the magnetization improves. So you can see it doubles even more than twice, and multiplies by factor 2, basically, the achieved magnetization. And the best composition is for 0.65% of iron. And here in the loop, you can see that we can generate this high magnetization. So if we calculate the saturation magnetization from this loop or from the moment versus time, we get these curves where basically you can see the maximum is at 0.65%, well, 65% of iron in this compound. And the cyclability for this material is very good even after 10 to the 3 cycles, even after 1,000 cycles. And like before, the starting material, iron cobalt nitride, is fully homogeneous, so that it's really let's say, a good mix of iron and cobalt. There are no clusters. But when we apply voltage, and these are the images here, you can see again planar front. And in this case, the nitrogen is accumulated at the top. So before I showed that in some material like iron nitride, the nitrogen was accumulated at the bottom, now here at the top. So sometimes the nitrogen goes at the bottom, sometimes at the top, and I will show you the reason for this towards the end of my presentation. But now I want to focus on 2 works actually that exist in the literature where people have moved nitrogen in solid state. So as I mentioned, most of our works are in liquid electrolyte gating, but there are some exceptions, and we have also studied what happens in solid state. But the first work actually in solid state is not from our group, it's from the group of Kai Liu. It dates back to 2023, and they studied the exchange bias effect between cobalt iron and manganese nitride. Manganese nitride is an antiferromagnetic material. Cobalt iron is ferromagnetic, They sandwiched this between the two tantalum layers, and they applied voltage. First, what they did is a heating and field cooling process to induce an interaction between cobalt ion and manganese nitride. A typical fingerprint of this interaction is the shift of the hysteresis loop, which is called exchange bias. And this phenomenon is actually very much used in spin valves and sensors nowadays in the computers. And there is exchange bias both at 10 Kelvin, but also at room temperature. And what happens here is that when you apply voltage, there are slight variations in the exchange bias. Okay, that was the first observation of modulating exchange bias in solid state in nitrides. And the reason for that is that when you anneal, there is some motion of nitrogen towards tantalum, because tantalum likes nitrogen a lot. And then when you apply voltage, there are slight changes in the concentration of nitrogen in the tantalum, and when you apply voltage, this nitrogen goes back to manganese nitride, and then you can modify the antiferromagnetic properties. In our group, what we studied is this cobalt manganese nitride single layer, again with the top and bottom tantalum layers. We applied voltage, and we again induced this exchange bias because cobalt manganese nitride is also an antiferromagnetic compound. Here we had some clusters of cobalt-3 nitrogen, cobalt-4 nitrogen that are ferromagnetic, and they were coupled to basically cobalt-2 nitrogen matrix, which is antiferro, especially below 30 Kelvin. And we saw this exchange bias, and when we apply voltage, we could change the magnetization, and we could change the coercivity and the exchange bias field, all at solid state. So now, next, what I want to show you is something funny, because we can induce this magnetoionic effect without contacting the sample with any wire. So we can induce this for wireless applications. So basically, we use a phenomenon from electrochemistry, which is called bipolar electrochemistry. In this case, we immerse our material, we place our material inside this liquid electrolyte. We have two platinum foils immersed in the liquid. We apply voltage between the two platinum foils, but the sample has no any electric contact. Okay? When we apply voltage to these two platinum electrodes, there is a phenomenon here in the material, which is actually titanium gold cobalt nitride, which is called bipolar electrochemistry. So what happens? Here is the positive platinum, and the part of the layer, the film, that is facing the positive platinum gets negatively polarized. And here on the other side, we have a positive induced charge. So this is a bipole, okay? Now, if this negative charge that is induced here through electrochemistry, bipolar electrochemistry, is sufficient to release the nitrogen away from cobalt nitride, we may be able to generate magnetism here. And actually, we did the experiment. I forgot to say that in this case, we introduce sodium iodine in the propylene carbonate, which is our electrolyte. And because this increases the strength of the ionic double layer, electric double layer, sorry. And that's why there is this yellow color, because there is a side reaction here in the positive platinum. But what is interesting is that in our film, on the right part of the film, we generate cobalt. And actually, you can see here shiny appearance, even optically, you can detect that it has been metallized. And we induce a clear ferromagnetic hysteresis loop. So the gas ground was paramagnetic. After applying 50 volts for 5 minutes to these two platinum electrodes, you can generate ferromagnetism. But here the problem of this configuration is that after some hours, the ferromagnetic response starts to decrease. Okay, and it starts to decrease because there is a diffusion back of nitrogen laterally, and this cobalt tends to get again nitrurated. So in order to minimize this, what we did is to change the configuration from horizontal configuration to vertical configuration. And now in this configuration, all the layer is exposed to this wire, to this bipolar electrochemistry. So we will release nitrogen from the whole film, actually here, this part. And eventually we thought that because now the distance between the negative and the positive is very narrow, maybe the effect is non-volatile. And actually, this is what happened. Now here you can see photos of the photograph of the experiment. We apply this voltage. You can see again the side reaction, this yellow color. And now the film, it all becomes like shiny, metallic-like. And we can modulate the magnetization, both with the time and the voltage. And you can see here for to different voltages, different times that we can, in an analog way, we can control the magnetization. And interestingly, if you stop the voltage, in this case, the magnetization remains even after 24 hours. So the effect now is non-volatile. So horizontal configuration volatile, vertical configuration permanent effect. Why is non-volatile? Because as I mentioned before, in the horizontal configuration, we have strong, this comes from simulation, strong difference of potential between the left and the right sides of the sample. When we stop the voltage, this tends to discharge, and this discharging causes the reverse reaction, and the nitrogen just moves laterally. Here, the difference of potential between the two sides of the sample is very small, and virtually there is no reverse reaction, and the effects are permanent. Again, here you can see this typical planar front of nitrogen Magneto-Ionics. Okay, next I want to focus on an application precisely of this planar front. So what we did now, so far, what I showed was continuous layers. What we did next is to pattern the system into small dots. So we used electron beam lithography to create these arrays of iron cobalt nitride dots that initially are paramagnetic. We immerse this sample in the electrolyte, and we measure by mode the magnetic properties as a function of time when we were gating, applying minus 25 volt. So this arrow here means increase of time, and this arrow here are the same, applying minus 25 volt and 25 volt positive. So starting from the paramagnetic state iron cobalt nitride, you can see that when we increase the time, there is first the creation of a square hysteresis loop that is typical of coherent rotation. And then as we increase further the time, we could see with Irena, actually the first co-author of the paper, that the loops get constricted and we increase the magnetization progressively. And then if we change the polarity, we start with this constricted loop, we go back to square loop, and finally paramagnetic. So the effect is fully reversible. And what happens here, the idea is that we start with paramagnetic state off. So we have a Magneto-Ionic switch like before, but tuning the kind of reversal. So we go from paramagnetic state to single domain state for thin iron cobalt. And then as the iron cobalt thickness increases, we form this vortex. This vortex state is a state in which the spins just follow the edge of the structure. So if we do MFM, what we would expect is at some point to lose the magnetic contrast. So we did do MFM for these two cases, 10 minutes and 150 minutes. And for short time, you can see square loop, and you can see this dipolar contrast, meaning is a single domain state that just rotates with time, with the magnetic field. However, for the thick iron cobalt, you can see that at some point, 0.3, where the magnetization is 0, we lose this dipolar contrast. We have this vortex. The formation of vortex was further confirmed by PIM in the synchrotron alpha, and we could also get some complex dependencies of the Kerr amplitude, saturation and annihilation field, and the coercivity, which I don't have time to explain here, but they correspond to different phases created in the material and the gradient of nitrogen across the dots. Okay, here, interestingly, we could again see this planar migration front, and we could see, so this is the starting material has grown, again homogeneous, and after gating, we could see accumulation of iron and cobalt at the bottom of the film and nitrogen at the top of the film. So now in the remaining time, what I want to show is that Magneto-Ionics can indeed be useful for synaptic applications. And first of all, I would like to remind you a bit what is neuromorphic computing and what are the requirements of materials for this effect. So neuromorphic computing refers to a device that artificially mimics the way of functioning of the brain. So basically, we want to have analog electronic circuits that mimic neurobiological circuits of the nervous system. In our case, the parameter that we want to tune is magnetization. So M in our case is magnetization, but you can think of it as memory. Now, materials to show these neuromorphic, let's say, synaptic functionalities and be able to be used in neuromorphic computing, they should show some properties. For example, plasticity. For example, a multi-state behavior, a threshold value of voltage, as in Magneto-Ionics, operation in milliseconds or faster. So far, I showed you sub-second, and now I will show you that we can do millisecond as well. It should show non-linearity, non-volatility, low energy, and so on. So Magneto-Ionic materials fulfill most of these requests. And now let me show you some examples. For example, here we have iron cobalt nitrate, 10 nanometer thick. Here the material again is paramagnetic, and we activated the ferromagnetic properties using different voltages, applied for 1.5 minutes. So if you apply -4 volt, you can see you induce a bit of change in the magnetization and then it relaxes. But if you apply higher voltage, you have a larger change in the magnetization. It also relaxes, but will retain better. So this is a property of biological synapses, which is called amplitude-dependent plasticity. Depending on the voltage that you apply, the synaptic weight can increase, as you can see here. Now, if we perform repeated stimulations of the material, we can get this nice multi-level, multi-state behavior, which is also needed in synaptic applications. Or you can play, for example, with the time. So here we keep the voltage -8 volt, and we change the time. So in the blue one, this one is just half a minute, and we induce something, but we retain just a little bit. As you can see, the non-volatile is just this part here. But if we increase the time that we're applying this voltage, we generate higher magnetization. We also forget something, but we retain better. So this property is called spike time dependent plasticity, and you can imagine it to make the analogy with the brain. For example, looking at a poster in a conference, if you look at it just half a minute, you will see something, you will remember some details of the poster, but not that much. But if you stare there at the poster for 100 to 2.5 minutes, you will remember much better what the poster was about. So you have learned better what the poster is about. And this property is mimicked here with Magneto-Ionics. Of course, we can induce cycles. We can do potentiation depression cycles up to more than 1,000. And here on the right, what I want to show is that this multi-level memory actually in Magneto-Ionics can be controlled with voltage, but it can also be controlled with magnetic field. So here you can see 3 cores for different voltages, and here we are changing the magnetic field. So this is something that membristors cannot do. Membristors are materials that are typically used in neuromorphic computing. There you can change the amplitude or the synaptic weight just with voltage. Here you can play with 2 degrees of freedom, voltage and magnetic field, adding extra functionalities. And finally, this is one of the last examples I want to talk about, is this Magneto-Ionic at fast rates. So here we studied cobalt nitride, and we have 2 films, 200 nanometers, 25 nanometers. Let's start with 200 nanometers. And here the DC is the conventional, let's say, continuous voltage that I have shown you before. But we can also induce Magneto-Ionics applying pulses between 0 - 25 volt at 1 Hertz, 10 Hertz, and 100 Hertz. Now, if we go slowly, like 100 Hertz, you can see that we induce very little effect. And why is that? Because each time we induce something, then when we stop the voltage at 0 volt, in this period of 0 volt, whatever we induce, it relaxes. And we induce again, it relaxes back. Induce, relaxes back. So the net effect is very small. But if we go fast, we induce the Magneto-Ionics faster, and then during this very little time, there's no time for relaxation. So actually, there's a cumulative effect here at 100 Hertz, and we can move from short-term memory, where here we induce just for, let's say, 1 Hertz, so basically 1 second, to long-term memory, where here the memory is permanent. Now, if we go to 25 nanometers film, there is an interesting effect that we were not expecting to see, but it's here. And actually, the effect is comparing these blue and red curves. So if we go very slowly, you can see these oscillations because of the cycles of the voltage gating. We induce and we suppress like this. If we apply this seam, what happens is that when we stop the voltage, the magnetization continues to increase. So actually, it's shown better here. This part, this up to 600 seconds, where the voltage is applied, we have this increase on magnetization, nothing new. But what is a bit surprising and strange is that when we stop the voltage, in the case of the red curve, it relaxes like before. But for when we apply this DC voltage, in this case, thin films, we have a post-stimulated learning. It is as if the memory gets consolidated and even enhanced without any stimuli. And this mimics a bit what happens in our brain when we go to bed, when we sleep. Actually, sleeping is very much needed for the memory to get consolidated. We need to sleep as human beings, we need to sleep. So what happens here, this increase in consolidation of memory, is related to some ion diffusion processes in the film, and maybe in the brain happens something similar. Maybe these ions need to get to some stable values while we are sleeping. So this is related to the accumulation of nitrogen at the top. So basically, what happens in cobalt nitrate at the beginning is that the nitrogen is released from the film to the liquid in a layer-by-layer fashion, so you will expect nitrogen to be accumulated at the bottom of the films. But if magnetoionics is very fast, for thin layers in particular, what happens is that at some point the nitrogen goes up, but all the propylene carbonate chains indicated here in blue get solvated with nitrogen ion. So basically we exceed the solubility limit of nitrogen in propylene carbonate. When this happens, the nitrogen cannot be further released to the liquid because we are exceeding the solubility limit, and we need to stop the voltage for new propylene carbonate chains to reach the interface and then take some additional nitrogen from the film, and then this allows to increase the magnetization further. So the fact that sometimes we see nitrogen at the top of the film is because when we go very fast, this nitrogen cannot be further released, and then we see it at the top. So basically, nitrogen at the top is a signature of fast magnetoionics, nitrogen at the bottom, slow magnetoionics. Okay, I would like now to point out some conclusions. I have shown you that we can induce on and off switching of ferromagnetism by nitrogen magnetoionics, that the effect is faster than for oxygen. We need lower onset voltages. There is a particularity of this material that there is this planar wave front, that at the beginning was a mere scientific curiosity, but later on we could use this to induce formation of magnetoionic vortices, or we call vortions. The magnetoionic effects can be also induced in a contactless manner. This is important maybe for biological applications in the future. And also, magnetoionics has potential for artificial synaptic functions. And with this, I would like to thank you all for your kind attention. Thank you very much.
Thank you, Jordi, very much for your presentation. We do have a question for you. Could you comment on the reversibility of magnetoionic systems?
Yeah, I have shown you. Maybe I should share again the slides. Am I sharing now the conclusions? Or yeah?
The whole slide, yeah, the conclusion, yeah. Thank you note.
Okay, well, there is the reversibility actually. For example, you can see in do you see now this one, for example? Here you can see the reversibility that happens in several of the slides. But for example, here, so it is reversible, but here it's just at 0 volts. So here we apply voltage, we induce some effect, we stop the voltage, and then it goes down. But later I showed you this complete reversibility applying voltage of opposite polarity. So this, for example, we induce at -8 volts, and then we apply positive 8 volts, and we have full reversibility that we can do even at 1000 seconds. The reversibility depends on the applied voltage. So if you apply too much voltage, like for example -50 volt, you will induce a lot of effect, and then even if you apply positive voltage, you will just reverse partially the material. So we want to have good cyclability or reversibility. We need to stick to relatively small changes of magnetization, and then you can modulate it reversibly.
Thank you, Jordi. And there is a follow-up question. So, are there other ions that contribute more effectively to the reversibility and long-term durability of these systems, or nitrogen is the best among all?
There are a lot of works with oxygen in the literature, especially if you have very thin layers of cobalt, for example, in contact with gadolinium oxide, where the effect, instead of a full oxidation reduction, is just adsorption at the interface, then it's much easier to reverse. So with oxygen you can do it, but provided that you don't fully oxidize or reduce. If you fully oxidize or reduce, then you have limitations because it's a full structural transition. With lithium, it's also possible. Actually, I showed an example of a skirmions from the group of Aalto in Finland, and they could do, again, this reversibility quite well. And there are other ions, for example, now protons, hydrogen ions, It's reversible, but then it depends on the humidity. So the problem there in this kind of experiments is that depending on the day, you may get different values of the induced magnetization. Actually, in their paper, they show that if they do the experiment in some other controlled atmosphere or under vacuum, the effects are different. And now in our group, we are exploring other ions actually. Now papers in archive, moving carbon, for example. You can also move carbon and do carbon magneto-ionics. So there are prospective applications with the other ions as well, especially when it goes into biomedicine.
Thank you very much, Jordi. Let me see if there are some other questions. Yes, we do have. Um, so magnetoionic materials often suffer from limited cyclability or endurance. So how many cycles a good magnetoionic material should withstand to be marketable?
Yeah, so for example, in our laboratory, we have reached several thousands of cycles. Probably you can induce more, but we just didn't do it. Maybe we can reach 10 to the 4, but it just takes a lot of time, more than 2 weeks maybe to do that, because this is not super fast. Huh? We are doing, in this case, seconds. Just think that, for example, the solid state drives that you can buy in the shop and we use to store data, they have an endurance of 10 to the 4. So in that sense, our magnetoionic material is close to that value. There are other materials where maybe combined action of ferroelectric and magnetoionics using bismuth ferrite that have shown even higher endurance, several 10 to the 4, even 10 to the 5, very close. Also, the group of Professor Beach in MIT using proton magnetoionics, they can do 10 to the 4 cycles. So that's a bit where we are now, state of the art.
Thank you very much, Jordi. Are there any other questions? There is. So, in line with what was said previously about the new applications, how do you see the future of magnetoionics? So, what are the most promising directions or applications you foresee for this field?
Yeah, I feel that, people at the beginning were trying to modulate the magnetic properties of films with magnetoionics for spintronics, for example. But magnetoionics is a bit slow. Now we are the fastest in the literature is about microseconds, something like that. So compared to spintronics, that is nanoseconds, this is slow. But you can use magnetoionics to just for the reconfiguration state. So you can then apply spintronics. If you want to change some property of the film, you apply one magnetoionics, you change the properties, and then you can again do your spintronic application. So for reconfiguring the magnetic properties, magnetoionics is good. In our group, we are now exploring magnetoionics for data security. We have now a paper in archive where we use these magnetoionics to generate probabilistic bits, for example. And as I have shown you in this presentation with some detail, you can use magnetoionics to mimic the brain. So maybe going into neuromorphic computing is a direction for magnetoionics because the brain also uses ions, is in a liquid, and we can, as I have shown, it can mimic the brain quite well. And our brain is not that fast. Our brain doesn't work in nanoseconds. Our brain works in milliseconds. And this speed is attainable even in our group with magnetoionic materials. So that's another potential application.
That's great to hear, Jordi. Thank you very much. If there are no more questions, I don't see. Of course, I invite people if they would like to raise their hand as well to ask directly. If not, Jordi, thank you so much for sharing your knowledge and all the findings with us.
You're
It's
welcome.
quite interesting and quite insightful. Um, it was indeed a great talk. Of course, for the ones that were not able to join us and the ones that join us a bit later, there will be a full recording of this webinar available on the NICKEFFECT YouTube channel as well as on the website and social media. And with this in mind, I would like to close and invite everyone to follow the NICKEFFECT's final year of our journey in developing novel ferromagnetic materials. So
I would like you to thank the organizers and the coordinator of NICKEFFECT, Aliona, for the very kind invitation to this webinar. Thank you very much.
you're welcome as well from all of our sides. Thank you very much, Jordi.
Thanks a lot.
Everyone, a lovely day, and we keep in touch. Bye bye.
Bye bye.